Hey, all, today we're going to talk a little more about probability, and we're going to start that with a discussion about theoretical probability. And this is something you probably are familiar with a little bit. So these are probabilities that are from mathematical models, and it's not just simply observing, so collecting data. So this is not flipping a coin personally. This is the theory or the theoretical probability if you did flip a coin. So this notation here says the probability of event A is equal to the number of outcomes in the event and the number of possible outcomes. So for example, let's bring up our card idea again. The probability of getting a face card. So that would be the number of face cards in a deck, like Jack, Queen, and King, divided by the total number of cards in a deck, 52. So we have 3 face cards in each suit. There's 4 suits. So there's 12 total face cards divided by 52 total cards. That gives us 3/13. So the probability of drawing a face card on any card drawn from a deck is 3/13. And this is what we'd call the long run relative frequency. So in theory, the probability of drawing a face card is 3/13. If we drew a card out of a deck like 1,000 times, maybe a couple thousand times, in the end, you should come down with getting a face card 3 out of every 13 tries. So there's important things to know about probability, formal probability. Sometimes we speak informally about probability. Somebody might be feeling not so good maybe about a test, and they might say, I've got a 40% chance of passing this test. Well, there's no statistical evidence behind that actual probability. It's just a feeling. It's informal. Informal probability, a probability of something happening is always between 0 and 1. So the probability of event A is greater than or equal to 0, less than or equal to 1. A probability of 0 means that it's never going to happen. A probability of 1 means that it's always going to happen. The set of all possible outcomes of a trial, when you add up all their probabilities, they need to total 1. So for example, the probability of getting a heads is 1/2. The probability of getting a tails is 1/2. Those are the only 2 possible outcomes of flipping a coin, and both of those probabilities add up to 1, or 100%. So the probability of your sample space is 1. If we know the probability of something happening, and we subtract that from the total possible probability of 1, we call that the complement, and that would be the probability that that thing doesn't occur. So the probability of picking a face card out of a deck is 3/13. So if we wanted to find the probability of picking a card that wasn't a face card, or not picking a face card, we would subtract 3/13 from 1, and you would get 10/13. So those are complements of each other. They're not complements in the sense that they're nice to each other. This is a math word like you use in geometry. So there it is in some technical speak. The probability of event A is equal to 1 minus the probability of the complement of A, which means A not happening. And then a Venn diagram that you should have seen something like this in the past. The circle represents event A. Everything else represents event A not happening. So let's do a little probability example here. You drive to work every day, and you go through the same light every day. And it's a busy intersection, and you find that 35% of the time the light is green, and you can drive right through. So we want to know, given that, what is the probability that the light is not green? So the light not being green is actually the complement. So the probability of A is equal to 1 minus the probability of the complement of A. And we know that the probability of a green light is 35% or 0.35. We want to know the probability of not a green light. I'll say no green. So we subtract 1 from both sides, and we get negative 0.65 equals negative probability of no green. And then some quick algebra tells you that the probability of having no green light is 0.65. So you can say that there's 65% of the time you arrive at this intersection, the light will not be green. So that means it could be yellow or red, but it's definitely not green. So another thing that happens with probabilities is we can talk about the addition rule. So I have a Venn diagram over here of two disjoint or mutually exclusive events. That means that they both can't occur at the same time. If that's the case for two events, if they're disjoint, if they're mutually exclusive, and we want to know the probability of one of them happening or the other one happening, then we could just add the probability of A to the probability of B. And real quick, all the way back from geometry, that symbol sort of represents or. So this is the probability of A or B. So let's do an example. We know that a green light happens 35% of the time. And now we're going to say that we get a yellow 4% of the time. We want to know the probability the light is red. So if the light is not red, then it's going to be green or yellow. So we can find the probability of the light being green or yellow. Oops, that actually looks like the word guy. I didn't plan that. So green or yellow, they're mutually exclusive because the light cannot be green and yellow at the same time. So I just add the probability of it being green plus the probability of it being yellow, which is 0.35 plus 0.4. And I get that it's going to not be red 39% of the time. So the probability that it is red, we can just do 1 minus the probability of green or yellow. Again, that doesn't say guy, it's green or yellow. So that's 1 minus 0.39 or 0.61. So 61% of the time, the light is going to be red. Another rule we have is the multiplication rule. This is when we want to know the probability of event A and B happening. So that means and. If these two events are independent, independent means that the outcome of one event does not affect the outcome of the other. If they're independent and I want to know the probability of one of them happening and the other one, I could just multiply those two probabilities together. The key thing here is that they have to be independent. So again, we're taking all this information now that we have of our traffic light, and we want to know the probability you hit a red light 2 days in a row. So hitting a red light on a Monday is not going to determine whether or not you hit a red light on a Tuesday. So the probability of hitting a red and a red is just the probability of hitting a red once times hitting it again. So we would do 0.61 times 0.61, since it's a 61% chance that you hit a red light. And we get that the probability of hitting a red light 2 days in a row is 0.37 approximately. So approximately a 37% chance that you hit a red light when you get to this intersection 2 days in a row. And we could keep doing this. We could find the probability of 4 days in a row, 5 days in a row. Getting a red light on one day does not predict whether or not you'll get a red light the next day, so they're independent. So we could just keep multiplying these together. So that's it for today. I got some practice up on the board. Make sure you get to it and ask me any questions if you have them.